Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the gentle precision of planetary exploration, where a single rover named Perseverance transforms Martian stone into scientific poetry. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On February 18th of 2021, Perseverance descends through Mars's whisper-thin atmosphere, its heat shield glowing cherry red as friction transforms the rover's cosmic velocity into thermal energy. The spacecraft's sky crane hovers 20 meters above the crater floor, lowering the six-wheeled laboratory on nylon cords as delicate as spider silk, yet strong enough to bear a metric ton of scientific ambition. The rover's wheels touch regolith that has waited 4 billion years for this mechanical visitor, fine particles of iron oxide and basaltic sand that rise and settle like rust-colored snow in the weak Martian gravity. Each grain of this ancient dust carries isotopic signatures of stellar nucleosynthesis, elements forged in supernovae that exploded when the solar system was still a nebula disk of gas and cosmic debris. Jezero Crater spreads beneath the rover's cameras in shades of ochre and umber, its 45-kilometer diameter holding secrets of an ancient lake that once lapped against delta deposits now frozen in stone. The crater's rim rises 2,000 meters above the landing site, a circular rampart carved by cosmic impact when Mars was young and water flowed freely across its surface. This collision occurred roughly 9 billion years ago, when an asteroid, perhaps 5 kilometers wide, struck the planet with energy equivalent to millions of hydrogen bombs, vaporizing rock and excavating a basin that would later fill with life-sustaining water. Perseverance sits at the bottom of this geological amphitheater, surrounded by rock formations that record the planet's transition from a warm, wet world to the cold desert it has become. The rover's radioisotope thermoelectric generator hums quietly, converting plutonium-238's decay heat into electrical current that will power scientific instruments for years to come. This nuclear heart beats with the steady rhythm of atomic transformation, each uranium nucleus splitting in perfect accordance with quantum mechanics, indifferent to Martian seasons or the vast distance from Earth. The isotope's half-life of 87 years ensures that the rover will maintain power long after its planned mission duration, continuing to generate electricity even if communication with Earth eventually ceases. Only took humanity 70 years to perfect nuclear batteries reliable enough for interplanetary missions, and somehow they still function flawlessly in temperatures that would freeze carbon dioxide solid. Scientists monitor the landing from mission control rooms where coffee grows cold and calculations sprawl across whiteboards, their excitement tempered by the 14-minute communication delay that stretches between worlds. Radio signals carrying news of the successful touchdown race outward at light speed, crossing the orbital paths of asteroids and comets before reaching antennas in California and Spain. The rover has arrived, but in some cosmic sense, Earth will not know this for another quarter hour, time enough for continental drift to shift the planet's surface by several atomic widths. This temporal disconnect means that every command sent to Perseverance must account for a Mars that will exist 28 minutes in the future when the response returns across the interplanetary void. Dust devils spiral across the crater floor in the Martian afternoon, their translucent columns lifting particles that may have been disturbed for the first time in millennia. These atmospheric whirlwinds follow thermodynamic principles identical to those governing Earth's tornadoes. Yet they move through air so thin that their fury would barely rustle paper in terrestrial conditions. The planet exhales these ghostly cyclones as its surface heats and cools, a respiratory rhythm measured in sols rather than hours. Each Martian day lasts 24 hours and 37 minutes, just long enough to throw off circadian rhythms for mission controllers, who must synchronize their sleep cycles with a world that turns slightly slower than their own. The rover's aluminum wheels press into regolith, composed of olivine, pyroxene, and feldspar minerals that crystallized in magma chambers when Mars possessed a molten core and active volcanism. These same compounds form the backbone of Earth's oceanic crust, yet here they rest exposed to cosmic radiation and temperature swings that would shatter granite. The regolith contains perchlorate salts that make the soil toxic to most Earth life, compounds that form when ultraviolet radiation breaks down atmospheric trace gases in the absence of a protective ozone layer. Mars has been sterilizing its own surface for billions of years, creating a chemical environment hostile to biology as we understand it. Perseverance carries 17 cameras, each engineered to withstand temperature variations from -80 to 0 degrees Celsius. Their lenses crafted from sapphire to prevent scratching by wind-borne particles. The rover's eyes perceive wavelengths invisible to human vision, detecting infrared thermal signatures and ultraviolet fluorescence that reveal mineral compositions hidden to optical observation. These instruments will spend the coming months photographing rocks that formed when Mars possessed a magnetic field strong enough to deflect solar wind, an atmospheric pressure dense enough to support liquid water, and perhaps even microbial ecosystems thriving in hydrothermal springs. The landing site lies at the western edge of a fan-shaped delta where an ancient river once deposited sediments into Jezeros's lake. This delta represents one of the most promising locations on Mars for finding preserved biosignatures, organic molecules, or mineral textures that might indicate past microbial activity. Orbital reconnaissance has identified clay minerals within the delta deposits, compounds that form only in the presence of water and often preserve organic chemistry with remarkable fidelity. Only took 3 decades of Mars exploration to locate such a perfect geological target, and now the planet's first astrobiological laboratory sits precisely where water once met land in conditions that might have supported life. The rover's nuclear generator radiates waste heat into the Martian night, warming critical electronics as ambient temperatures plummet below the freezing point of carbon dioxide. This thermal management system operates like a planetary metabolism, circulating heat through insulated compartments that house spectrometers, computers, and communication equipment worth more than some national space programs. Each component has been tested in thermal vacuum chambers that simulate conditions more hostile than any earthly environment. Yet here on Mars, they must function flawlessly for years while exposed to cosmic radiation that would prove lethal to unprotected human explorers. The rover's cameras begin their patient survey of Jezero crater at dawn, when shadows stretch long across sedimentary formations that rise like ancient architecture from the crater floor. These layered rocks tell stories written in stone over millions of years, each stratum a page in Mars's hydrological history when liquid water carved channels through volcanic highlands and deposited clay-rich sediments in standing lakes. The delta formation spreads before Perseverance like a fossilized river mouth, its fan-shaped deposits containing minerals that formed only in the presence of sustained aqueous environments. Orbital spectrometers have detected phyllosilicates within these rocks, clay minerals that require water molecules to incorporate into their crystal lattices. Geological proof that this crater once held a lake deep enough to support complex sedimentary processes. The morning light reveals rock textures invisible to orbital reconnaissance, fine-grained layers that suggest seasonal deposition cycles when Mars experienced climate variations driven by orbital mechanics and axial precession. These sedimentary bands alternate between light and dark compositions, indicating changes in the source material transported by ancient rivers that fed into Jezero's lake system. Some layers contain iron oxides that formed in oxidizing conditions, while others preserve sulfur-bearing minerals that precipitated from evaporating brines under reducing atmospheric chemistry. The rover's cameras capture these variations in exquisite detail, each pixel representing scientific data that will occupy researchers for decades as they reconstruct environmental conditions on a planet that lost its habitability billions of years before complex life emerged on Earth. Perseverance's Mastcam-Z instrument photographs the delta's exposed face through multiple spectral filters, revealing mineral distributions invisible to human perception. Iron-bearing compounds appear in false color images as purple and blue signatures, while clay minerals glow in infrared wavelengths that penetrate Mars' dusty atmosphere. These phyllosilicates likely formed when volcanic rock weathered in the presence of liquid water, their layered crystal structures trapping molecules and ions from the ancient Martian environment. Scientists theorize that such clay deposits could preserve organic compounds for geological timescales, protecting potential biosignatures from the harsh radiation and oxidizing chemistry that characterizes modern Mars. The delta's stratified architecture extends vertically for dozens of meters, representing perhaps millions of years of continuous deposition when rivers flowed consistently enough to transport sediments across hundreds of kilometers. This persistence suggests that early Mars maintained stable climatic conditions far longer than previous models predicted, with atmospheric pressure dense enough to prevent liquid water from immediately boiling away at the planet's surface. The rover observes these formations from multiple angles as Martian sunlight shifts throughout the sol, revealing subtle textural variations that indicate changes in water flow velocity, sediment grain size, and depositional environment over geological time. Each sedimentary layer captures a moment in planetary history when Mars possessed characteristics more similar to Earth than to its current frozen state. The rocks record evidence of meandering river channels, seasonal flooding events, and periods of lake-level fluctuation that mirror terrestrial sedimentary environments in remarkable detail. These parallels suggest that early Mars operated under similar physical principles to Earth's hydrological cycle, with precipitation patterns, evaporation rates, and erosion processes governed by thermodynamic laws that remain constant throughout the universe. Only took 4 billion years for these sediments to transition from active aqueous deposition to freeze-dried preservation in the Martian desert. The rover's navigation cameras detect small-scale features within the delta deposits, cross-bedded layers that indicate flowing water, ripple marks preserved in ancient mudstone, and channel structures carved by currents that carried sediments from highlands to the crater floor. These textures provide quantitative information about past water velocities, flow directions, and seasonal variations in the hydrological system that once sustained Jezero's lake. Paleocurrent analysis of these sedimentary structures will eventually reveal the location of the river's source region, perhaps identifying specific volcanic provinces where weathering processes generated the clay minerals now preserved in the delta deposits. The images reveal mysterious dark-toned rocks scattered across the delta's surface, materials that appear distinct from the surrounding sedimentary layers and may represent meteorite fragments or volcanic clasts transported by ancient floods. These exotic rocks pose intriguing questions about Mars's bombardment history during the late heavy bombardment, when asteroid impacts delivered both destruction and potentially life-sustaining organic compounds to planetary surfaces throughout the inner solar system. Some researchers speculate that meteoritic material could have provided essential elements for prebiotic chemistry, seeding early Mars with carbon compounds and catalytic minerals necessary for the emergence of life. Perseverance photographs the delta formation through multiple sols, capturing subtle changes in lighting conditions that reveal additional structural details within the sedimentary layers. The low-angle illumination of Martian sunrise and sunset creates dramatic contrasts that highlight bedding planes, erosional unconformities, and compositional boundaries invisible under direct overhead lighting. These variations in rock texture and mineral content record environmental transitions that occurred as Mars's climate evolved from warm and wet to cold and dry, preserving a geological record of planetary transformation unparalleled in the solar system. The rover's stereo imaging capabilities generate three-dimensional models of the delta deposits, allowing scientists to measure layer thicknesses, calculate depositional volumes, and estimate the duration of individual sedimentary cycles. These quantitative analyses suggest that Jezero's lake system persisted for millions of years, far longer than required for simple geochemical processes, but potentially sufficient for biological evolution if microbial life ever emerged on early Mars. The sedimentary record implies stable environmental conditions that could have supported ecosystems similar to extremophile communities found in Earth's most inhospitable environments. Morning shadows retreat across the crater floor as Mars rotates toward its slightly more distant sun, revealing additional sedimentary exposures that extend beyond the main delta formation. These outlying deposits suggest that Jezero's ancient lake was even larger than orbital surveys indicated, perhaps covering much of the crater floor during periods of high water levels when climate conditions favored enhanced precipitation and reduced evaporation rates. The rover will spend months investigating these peripheral sedimentary units, searching for evidence of shoreline processes, wave action, and biological activity in environments where water chemistry might have concentrated organic compounds and essential nutrients. The drill awakens with mechanical precision on Sol 47, its tungsten carbide bit beginning a slow rotation that will penetrate deeper into Martian rock than any previous mission has achieved. This percussion system operates like a miniature jackhammer, delivering controlled impacts at frequencies that would shatter earthly stone, yet prove perfectly calibrated for the basaltic compositions that dominate Mars's ancient crust. The drill's first target rests within a formation scientists have designated Mars, a Navajo word meaning Mars, honoring the indigenous knowledge systems that have observed planetary motions for millennia before telescopes revealed other worlds as geological entities rather than wandering stars. Perseverance approaches the selected rock with deliberate patience, its robotic arm extending instruments that will analyze the drilling site before any penetration begins. The PIXL spectrometer maps elemental compositions across the rock's weathered surface, detecting iron, magnesium, and silicon signatures that indicate igneous origins formed in primordial magma chambers when Mars possessed active volcanism. These basaltic rocks crystallized approximately 3.6 billion years ago, when the planet's molten core generated magnetic fields strong enough to deflect solar wind and maintain atmospheric pressure sufficient for liquid water stability. The rover examines textures invisible to orbital reconnaissance vesicular structures where gas bubbles once escaped from cooling lava, phenocryst minerals that formed at depth before volcanic eruption, and alteration products that developed during subsequent exposure to aqueous environments. The drilling operation begins with whisper-quiet efficiency, the bit advancing millimeter by millimeter through rock matrix that has remained undisturbed since the Archean eon. Each rotation removes microscopic fragments that fall into collection chambers designed to preserve sample integrity during the months-long journey back to Earth that awaits in some distant future mission. The drill encounters varying resistance as it penetrates different mineral phases, softer olivine crystals that formed early in the magma's cooling history, harder pyroxene grains that crystallized at intermediate temperatures, and plagioclase feldspar that solidified last as volcanic temperatures dropped below critical thresholds. These mineralogical variations record cooling rates, magma composition, and eruption style with precision that rivals laboratory analyses of terrestrial volcanic rocks. The rover's engineers programmed drilling parameters based on extensive testing in Mars simulation chambers, where prototype bits carved through meteorite samples under atmospheric pressures and temperatures that mirror conditions at Jezero crater. These preparatory experiments revealed optimal rotation speeds, percussion frequencies, and advance rates that maximize sample recovery while minimizing bit wear over multiple drilling operations. The system must function flawlessly despite temperature cycles that swing from -80 degrees Celsius during Martian winter nights to 0 degrees during summer afternoons. Thermal variations that would crack most earthly machinery, yet prove routine for equipment designed to explore other worlds. Rock powder accumulates in the drill bit's fluted channels, fine particles that preserve chemical and isotopic signatures of Mars' volcanic history with remarkable fidelity. These samples contain trace elements that reveal magma source regions deep within the Martian mantle, providing insights into planetary differentiation processes that occurred during the solar system's first 100 million years. Chromium, nickel, and platinum concentrations indicate whether the parent magma originated from primitive mantle compositions or evolved through fractional crystallization processes similar to those that generate terrestrial oceanic basalts. Only took 60 years of space exploration to develop drilling technology capable of coring alien rocks with sufficient precision to preserve delicate mineral textures and trace element signatures. The drilling process encounters unexpected resistance at depths where orbital surveys detected hydrated mineral signatures, suggesting that water-rock interactions altered the original igneous assemblage in complex ways that require direct sampling to understand. These alteration zones may preserve evidence of ancient hydrothermal systems where hot groundwater circulated through fractured bedrock, creating chemical environments potentially suitable for extremophile microorganisms. The drill bit must penetrate through multiple phases of mineral replacement and secondary precipitation, each representing different episodes in Mars's hydrological evolution as the planet transitioned from volcanic activity to impact bombardment to eventual desiccation. Vibrations from the drilling operation travel through the rover's chassis and into seismic monitoring equipment that records subsurface structure with unprecedented detail. These mechanical waves reveal the presence of fracture networks, void spaces, and compositional boundaries within the bedrock that extends beneath Jezero's sedimentary cover. The data suggests that ancient impact events created extensive fracture systems that later served as conduits for groundwater circulation, perhaps connecting surface water bodies to deep aquifer systems that persisted long after atmospheric conditions became hostile to surface liquid water. Such subsurface environments represent some of the most promising targets for future astrobiological investigations on Mars. The drill's sample acquisition system operates through ingenious mechanical design, using spring-loaded mechanisms to capture rock cores within hermetically sealed titanium tubes that will preserve atmospheric conditions and prevent contamination during eventual transport to Earth laboratories. Each tube measures 13 centimeters in length and 3 centimeters in diameter, dimensions precisely calculated to accommodate analytical requirements for advanced mass spectrometry, electron microscopy, and isotopic analysis techniques that exceed the capabilities of any rover-mounted instruments. These samples represent the first materials from another planet specifically collected for return to Earth, where they will undergo scrutiny from analytical methods not yet invented. Temperature sensors within the drilling assembly monitor thermal conditions that could affect sample preservation, ensuring that friction heating does not alter volatile compounds or degrade organic molecules that might preserve biosignatures from ancient Martian environments. The drilling operation maintains temperatures below critical thresholds through careful control of advance rates and rotation speeds, preventing thermal decomposition of mineral phases that formed under specific pressure and temperature conditions billions of years ago. Such precision requires constant monitoring of dozens of parameters that must remain within narrow tolerances throughout the multi-hour drilling sequence. The completed borehole extends 1 centimeters into bedrock, a modest penetration that nonetheless represents a profound achievement in interplanetary exploration and robotic engineering. This cylindrical void now connects Mars's surface to subsurface layers that have remained isolated from atmospheric chemistry and cosmic radiation for geological timescales, creating a window into pristine rock compositions that preserve original igneous textures and any subsequent alteration products. The rover seals this borehole immediately after sample collection, preventing atmospheric contamination of the exposed subsurface materials that future missions might wish to investigate with even more sensitive analytical techniques. PIXL's X-ray spectrometer awakens with electron beam precision, its tungsten target glowing at temperatures that would melt copper as high-energy photons cascade into rock matrices that have waited billions of years for this moment of atomic interrogation. The instrument's name unfolds into Planetary Instrument for X-ray Lithochemistry, a designation that barely captures the elegant physics occurring within its compact housing as characteristic X-rays emerge from excited atoms like fingerprints of elemental identity. Each photon carries information encoded at the quantum level, revealing not merely which elements compose the Martian rock, but their precise concentrations, oxidation states, and spatial distributions across microscopic domains invisible to any camera or human eye. The spectrometer's beam focuses to a spot smaller than a grain of sand. Yet this tiny illuminated area contains millions of atoms whose electrons dance between energy levels according to principles first described by Niels Bohr in his revolutionary model of atomic structure. When high-energy X-rays strike silicon atoms within feldspar crystals, they eject inner shell electrons with characteristic energies that depend entirely on the element's position in the periodic table. The resulting electron holes fill immediately as outer electrons cascade inward, releasing fluorescent X-rays whose wavelengths serve as atomic signatures more reliable than any human identification system. PIXL detects these secondary photons with silicon drift detectors cooled to temperatures approaching absolute zero, achieving energy resolution sufficient to distinguish between iron in different oxidation states or sulfur bound to various mineral phases. The rover positions PIXL sensor head mere millimeters from the rock surface, close enough that atmospheric absorption becomes negligible despite Mars's thin carbon dioxide envelope. This proximity reveals elemental distributions that orbital spectrometers cannot resolve, mapping chemical variations across individual mineral grains and detecting trace elements present at concentrations measured in parts per million. The spectrometer discovers titanium concentrations that indicate high-temperature crystallization from primitive basaltic magmas, chromium abundances suggesting mantle source regions similar to those beneath Earth's mid-ocean ridges, and nickel signatures that point toward meteoritic contamination during the late heavy bombardment when asteroid impacts delivered extraterrestrial materials to planetary surfaces throughout the inner solar system. Each measurement requires several minutes of photon accumulation as PIXL builds statistically significant datasets from individual X-ray events detected by its semiconductor arrays. The instrument operates in counting mode, registering each fluorescent photon as a discrete pulse whose amplitude corresponds directly to the original X-ray energy and therefore the emitting element's atomic number. This quantum counting approach achieves sensitivity levels impossible with earlier X-ray fluorescence systems, detecting elements present at trace concentrations that nonetheless provide crucial information about magma evolution. aqueous alteration, and potential biological processes that might have influenced rock chemistry during Mars's more clement past. The spectrometer's scanning capabilities generate two-dimensional chemical maps that reveal mineral associations invisible to optical imaging, distinguishing between primary igneous phases and secondary alteration products formed during subsequent water-rock interactions. These elemental distributions show where olivine crystals underwent serpentinization in the presence of liquid water, transforming iron-magnesium silicates into hydrated minerals that preserve evidence of ancient aqueous environments. PIXL detects sulfur concentrations that indicate evaporate formation during lake desiccation events, calcium abundances suggesting carbonate precipitation under alkaline conditions, and phosphorus signatures that might represent biological accumulation processes similar to those observed in terrestrial stromatolites and microbial mats. The instrument's analytical precision reveals isotopic information through careful measurement of X-ray fine structure, detecting subtle energy shifts that indicate different atomic masses within the same element. These mass variations provide insights into nuclear processes that occurred during stellar nucleosynthesis, planetary differentiation, and potentially biological fractionation if life ever emerged on early Mars. Iron isotope ratios recorded in magnetite grains might preserve signatures of bacterial iron reduction, while sulfur isotope compositions could indicate biological sulfate reduction in ancient hydrothermal systems, where chemosynthetic organisms thrived in the absence of photosynthetic primary production. PIXL's measurements occur against a background of cosmic radiation that constantly bombards Mars's surface in the absence of a protective magnetic field, requiring sophisticated data processing algorithms that distinguish between genuine X-ray fluorescence signals and spurious photon events generated by galactic cosmic rays and solar energetic particles. The instrument's shielding and electronic filtering systems reject most of this background noise, yet occasional high-energy particle impacts create spectral artifacts that must be identified and removed from analytical datasets. Only took 40 years of X-ray astronomy and planetary science to develop detection systems robust enough to perform precision elemental analysis on another planet while exposed to radiation levels that would quickly degrade unprotected semiconductor devices. The spectrometer operates through temperature cycles that would destroy most terrestrial laboratory instruments, maintaining calibration accuracy despite thermal expansion and contraction of its metal housing and semiconductor components. Internal heating elements warm critical electronics during Martian winter nights when ambient temperatures approach the freezing point of carbon dioxide, while thermal radiators dissipate excess heat during summer afternoons when direct solar heating could damage temperature-sensitive detectors. This thermal management system consumes precious electrical power from the rover's nuclear generator, yet proves essential for maintaining analytical precision throughout the multi-year mission duration. Each PIXL analysis generates datasets containing thousands of individual X-ray events, requiring onboard data processing algorithms that identify elemental peaks, calculate concentrations, and compress information for transmission across interplanetary distances. The raw data files would overwhelm communication systems if transmitted in their entirety, necessitating sophisticated compression techniques that preserve essential analytical information while reducing file sizes by factors of 10 or more. These processed datasets travel at light speed across the solar system, carrying elemental information from rocks that formed when Earth was still a volcanic planet without continents, oceans, or any trace of biological activity. The instrument reveals chemical heterogeneity within individual rock samples, detecting compositional variations that reflect complex cooling histories as magma crystallized in subsurface chambers before eventual eruption onto Mars' ancient surface. Some mineral grains preserve primitive compositions that formed early in the crystallization sequence, while others show evidence of late-stage fractionation processes that concentrated incompatible elements in residual melts. These petrogenetic insights provide constraints on magma chamber processes, volcanic eruption styles, and crustal evolution during Mars' Noachian period, when the planet possessed active tectonism and widespread volcanic activity that rivals Earth's most productive igneous provinces. SuperCam's laser awakens with the intensity of a miniature star, focusing infrared energy into pulses that last mere nanoseconds, yet carry sufficient power to vaporize rock surfaces and create plasma temperatures exceeding 10,000 Kelvin. This laser-induced breakdown spectroscopy system operates from the rover's mast like a mechanical sniper, targeting rocks up to 7 meters away with precision that rivals human marksmen despite operating through thin Martian atmosphere that scatters light in ways unknown on Earth. The instrument's acronym unfolds into SuperCamera. Though this modest designation barely captures the sophisticated physics occurring when coherent photons interact with matter at energy densities that transform solid basalt into luminous gas clouds containing atomic species in excited electronic states. Each laser pulse delivers energy equivalent to a lightning bolt compressed into temporal and spatial scales that challenge human comprehension, creating plasma conditions similar to those found in stellar atmospheres where nuclear fusion transforms hydrogen into heavier elements. The vaporized rock expands as a shockwave that propagates through Mars's thin carbon dioxide atmosphere at velocities approaching the speed of sound, generating acoustic signatures that the rover's microphone records as the first intentional sounds captured from another planet. These plasma formation events occur in microseconds, yet their spectroscopic signatures persist long enough for SuperCam's optical systems to analyze the characteristic emission lines that identify specific elements and their ionization states within the expanding vapor cloud. The spectrometer's 3 optical channels simultaneously record ultraviolet, visible, and near-infrared wavelengths emitted by excited atoms as their electrons cascade between quantum energy levels according to selection rules that govern atomic transitions throughout the universe. Each element produces unique spectral fingerprints determined by electron shell configurations that remain constant regardless of whether the atoms exist within terrestrial laboratories or Martian rock surfaces exposed to cosmic radiation for billions of years. Hydrogen emission appears at 656 nanometers with distinctive Balmer series characteristics, while helium produces lines at wavelengths that reveal isotopic compositions inherited from solar wind implantation during periods when Mars lacked atmospheric protection against charged particle bombardment. The laser targeting system operates through sophisticated optical alignment that compensates for atmospheric refraction, thermal expansion of the rover's mast, and mechanical flexure that occurs as Perseverance traverses the uneven terrain of Jezero crater. Engineers programmed pointing algorithms that account for the 17-minute round-trip light time between Earth and Mars, ensuring that target acquisition commands remain accurate despite the planetary motions that continuously alter the geometric relationship between mission control and the rover's position. This remote operation requires predictive modeling of Mars's orbital mechanics and rotational dynamics with precision that exceeds most terrestrial surveying applications, yet functions flawlessly across interplanetary distances that dwarf any earthly engineering project. SuperCam's plasma spectroscopy reveals elemental abundances invisible to other analytical techniques, detecting trace metals and rare Earth elements that provide insights into magma source regions deep within Mars' mantle and core mantle boundary processes that operated during planetary differentiation. The instrument identifies titanium concentrations that indicate crystallization temperatures and oxygen fugacity conditions during igneous formation, chromium abundances that suggest spinel saturation and mantle partial melting degrees, and vanadium signatures that reflect redox conditions in ancient Martian magma chambers. These trace element patterns match specific meteorite classifications, confirming that shergotite, nachlite, and chasignite samples already present in terrestrial laboratories indeed originated from Mars through impact ejection processes that launched rocks across interplanetary space with sufficient velocity to escape planetary gravity. The laser's repetition rate allows rapid analysis of multiple targets within individual rocks, creating chemical maps that reveal mineral zonation, alteration patterns, and textural relationships that formed during complex geological histories spanning billions of years. Each pulse removes nanometer-scale layers from the rock's surface, progressively exposing fresh mineral faces that preserve primary igneous compositions beneath weathered rinds modified by atmospheric chemistry and cosmic radiation damage. This depth profiling capability distinguishes between surface contamination and pristine rock chemistry, providing access to unaltered materials that retain original crystallization signatures from Mars' earliest volcanic epochs. The spectrometer detects hydrogen emission lines that indicate hydrated mineral phases formed during ancient water-rock interactions, revealing the spatial distribution of phyllosilicates and other alteration products that require aqueous environments for their formation. These hydrogen signatures appear strongest within fracture systems and vesicular zones where groundwater circulation, concentrated clay minerals, and evaporate deposits during periods of active hydrological cycling. SuperCam's analysis confirms orbital observations of hydrated minerals while providing ground truth validation for remote sensing interpretations that guided the rover's landing site selection and traverse planning throughout Jezero crater's sedimentary formations. The instrument's microphone captures acoustic waves generated by laser rock interactions, recording sound propagation characteristics that reveal information about rock porosity, fracture density, and mechanical properties that influence erosion rates and weathering processes on Mars. These acoustic measurements provide constraints on rock strength and brittleness that help interpret landscape evolution and the formation of sedimentary structures preserved within Jezero's ancient delta deposits. The sound waves travel through Martian atmosphere with velocities modified by temperature, pressure, and gas composition, creating audio recordings that document environmental conditions during each analytical session with temporal resolution unachievable through other measurement techniques. Plasma formation requires overcoming ablation thresholds that depend on rock composition, mineral grain size, and surface roughness characteristics that vary significantly between different geological units within the crater. Basaltic rocks vaporize more readily than quartzite or carbonate compositions, while vesicular textures and fracture networks influence energy coupling efficiency and plasma propagation dynamics. These material property variations affect spectral line intensities and plasma temperature evolution, requiring sophisticated calibration procedures that account for matrix effects and interference phenomena that complicate quantitative elemental analysis of unknown samples. The laser system operates through thousands of firing cycles without degradation, its solid-state components engineered to withstand thermal cycling, mechanical vibration, and radiation exposure that would destroy conventional optoelectronic devices within months of Martian surface operations. Each laser pulse consumes electrical energy equivalent to charging a smartphone battery, yet the system's efficiency approaches theoretical limits for converting stored electrical power into coherent optical radiation. Only took 30 years of laser development and space qualification testing to produce systems reliable enough for interplanetary deployment while maintaining spectroscopic precision comparable to terrestrial laboratory instruments. SuperCam's analytical capabilities extend beyond elemental composition to include molecular detection through Raman spectroscopy, identifying specific mineral phases and potentially organic compounds through their characteristic vibrational signatures. This combined approach provides comprehensive chemical characterization that links elemental abundances to specific mineralogical contexts, revealing formation processes and environmental conditions with unprecedented detail for planetary surface operations conducted through robotic proxies separated from their human operators by hundreds of millions of kilometers. Marley's lens descends toward the Martian surface with the deliberate precision of a surgeon preparing for microscopic examination. Its focusing mechanisms adjusted to reveal crystalline worlds invisible to human eyes, yet preserved with geological fidelity since the Archean eon. The Mars hand lens. Imager operates like a mechanical botanist studying alien flowers, except these specimens consist of olivine phenocrysts, pyroxene chains, and plagioclase laths that crystallized in magma chambers when Earth possessed no continents, and life existed only as primitive prokaryotic cells floating in primordial oceans. Each photograph captures textures that record cooling rates, crystallization sequences, and post-formation alteration processes with resolution approaching the limits of optical physics, revealing mineral relationships that require laboratory-grade petrographic analysis to interpret fully. The camera's macro capabilities transform mundane rock surfaces into landscapes of geometric beauty, where hexagonal basalt columns appear as crystalline architecture and vesicular textures resemble lunar craters frozen in volcanic glass. These close-up images reveal details invisible to orbital reconnaissance, the delicate filigree of dendritic crystal growth, the smooth curves where mineral grains adjusted their boundaries during slow cooling, and the angular fractures where thermal stress or impact events shattered pristine igneous textures into fragments that tell stories of planetary violence and geological time. Marley photographs. Individual crystals measuring mere millimeters across. Yet these tiny mineral grains preserve chemical signatures that connect Mars's volcanic history to processes operating within stellar cores, where heavy elements formed through nucleosynthesis billions of years before the solar system condensed from interstellar dust. The instrument's illumination system bathes rock surfaces in wavelengths calibrated to reveal compositional variations that appear invisible under natural sunlight, using light-emitting diodes that produce consistent spectral output despite temperature fluctuations that would alter the color balance of incandescent sources. These artificial lighting conditions eliminate shadows and surface reflections that obscure textural details, creating photographs with scientific utility that exceeds artistic considerations, yet nonetheless possess aesthetic qualities that inspire wonder at the geometric perfection inherent in crystallographic processes. The images document how atoms self-organize into ordered lattices according to thermodynamic principles that operate identically throughout the universe, creating mineral structures indistinguishable from their terrestrial counterparts despite forming under atmospheric and gravitational conditions vastly different from Earth. Each photograph requires careful focus adjustment as the camera approaches rock surfaces with positioning accuracy measured in fractions of millimeters, ensuring that depth of field encompasses the specific textural features targeted for scientific analysis. The autofocus system operates through contrast detection algorithms that identify sharp edges and high-frequency spatial variations characteristic of crystal boundaries, vesicle rims, and fracture surfaces that preserve evidence of formation processes and subsequent modification events. This mechanical precision functions despite thermal expansion effects that alter the physical dimensions of the camera housing and focusing mechanisms as Martian temperatures cycle between extremes that would crack most terrestrial optical equipment within days of exposure. Marley's stereo imaging capabilities generate three-dimensional reconstructions of rock surfaces that reveal topographic relationships invisible in single photographs, measuring grain sizes, vesicle distributions, and surface roughness characteristics with sub-millimeter accuracy. These quantitative textural analyses provide constraints on cooling histories, volatile exsolution processes, and erosion rates that shape the rocks after their initial formation through volcanic or impact processes. The stereo measurements distinguish between primary igneous textures formed during crystallization and secondary features developed during subsequent weathering, alteration, or mechanical abrasion by windborne particles during billions of years of atmospheric transport. The camera documents color variations that reflect compositional differences between mineral phases, revealing oxidation states, trace element substitutions, and alteration products that formed during water-rock interactions in ancient hydrothermal systems. Iron-bearing minerals appear in shades of red and brown that indicate different degrees of oxidation, while titanium-rich phases produce blue and purple hues characteristic of ilmenite and rutile crystallization under reducing conditions. These color patterns provide qualitative insights into formation environments and subsequent modification processes that complement quantitative analyses performed by PIXL and SuperCam spectrometers operating from different spatial scales and analytical perspectives. The instrument's dust removal tool precedes most imaging sessions, using compressed gas stored in titanium reservoirs to blow away accumulated particles that obscure rock surfaces and interfere with optical clarity. This pneumatic cleaning system removes dust layers that accumulate continuously as global dust storms transport fine particles across vast distances, coating exposed surfaces with iron oxide films that mask underlying mineral compositions and textural relationships. The dust removal process reveals fresh rock faces that preserve original crystallization textures and alteration products without contamination from atmospheric particulates that could confuse interpretations of primary geological processes. Matchley photographs reveal microscopic features that suggest biological processes might have influenced rock formation or subsequent alteration, including laminated structures reminiscent of terrestrial stromatolites, spherical features that resemble fossil microorganisms, and mineral precipitates with morphology similar to those produced by bacterial iron oxidation or sulfate reduction. These potentially biogenic features require careful documentation and eventual laboratory analysis to distinguish between authentic biosignatures and abiotic processes that can produce remarkably similar textures through purely geochemical mechanisms. The camera's resolution approaches the size scales where microbial life operates, making it theoretically capable of imaging preserved cellular structures if such features survive the harsh radiation and oxidizing chemistry that characterizes modern Mars. The imaging system operates through sophisticated data compression algorithms that reduce file sizes while preserving essential textural information for transmission across interplanetary distances at data rates constrained by power limitations and communication windows. Each high-resolution image contains millions of pixels that must be processed, analyzed, and transmitted using computational resources comparable to early personal computers, yet engineered to function flawlessly in radiation environments that would destroy consumer electronics within hours of exposure. These technical constraints require careful selection of imaging targets and compression parameters that maximize scientific return while operating within the physical limitations imposed by deep space communication systems. Close-up photography reveals the intimate relationship between form and function that characterizes mineral crystallization processes, where atomic scale interactions produce geometric patterns visible at macroscopic scales through emergent properties of self-organization and thermodynamic equilibrium. Individual crystal faces display stepped growth features where molecular addition occurred layer by layer according to surface energy minimization principles, creating terraced landscapes that record the specific temperature and chemical conditions present during formation. These crystallographic details provide windows into ancient environments that existed when Mars possessed active volcanism and perhaps even primitive life forms, exploring ecological niches in hydrothermal springs and alkaline lakes. The camera documents weathering processes that continue to modify rock surfaces through wind abrasion, thermal cycling, and chemical alteration despite the planet's current hostile environment, revealing how geological processes operate under conditions vastly different from terrestrial weathering systems. Aeolian erosion creates streamlined forms and ventifact textures that indicate prevailing wind directions and velocities, while thermal fracturing produces polygonal crack patterns that reflect daily temperature variations and seasonal thermal cycling. Only took 6 decades of planetary exploration to develop imaging systems capable of documenting geological processes on other worlds with resolution sufficient to distinguish between formation mechanisms that operated billions of years apart. The first cached sample slides into its titanium tube with mechanical finality. A cylindrical piece of Mars measuring 13 centimeters in length and containing approximately 15 grams of ancient rock that has journeyed from magma chamber to interplanetary storage within the span of a single sol. This hermetically sealed container represents humanity's first successful attempt to collect pristine geological specimens from another planet specifically for return to Earth laboratories, where analytical capabilities exceed rover-mounted instruments by orders of magnitude in sensitivity, precision, and molecular detection limits. The sample acquisition system operates through ingenious engineering that captures solid rock cores while preventing atmospheric contamination and preserving volatile compounds that might degrade during the months or years required for eventual transport across the solar system. Perseverance's caching mechanism functions like a robotic pharmaceutical laboratory, maintaining sterile conditions and controlled atmospheres that protect sample integrity from the moment of collection through final sealing and storage operations. The titanium tubes resist corrosion by perchlorate-rich Martian soils and provide electromagnetic shielding against cosmic radiation that continuously bombards the planet's surface in the absence of a protective magnetic field. Each container undergoes leak testing and pressure verification to ensure airtight seals that will preserve internal conditions during thermal cycling. Mechanical vibration and acceleration forces that accompany interplanetary transfer trajectories and atmospheric entry procedures on multiple worlds. The cached rock originates from the Rochette Formation, a fine-grained basaltic unit that crystallized approximately 6 billion years ago when Mars experienced active volcanism and possibly maintained surface conditions suitable for liquid water stability. This particular sample contains vesicular textures that indicate gas exsolution during volcanic eruption, preserving evidence of ancient atmospheric compositions and volatile cycling processes that operated during the planet's early geological evolution. The vesicles themselves represent time capsules that trapped atmospheric gases within cooling lava flows, creating microscopic reservoirs that might contain isotopic signatures of primordial Martian atmosphere before photochemical processing and solar wind erosion modified the planet's gas inventory. Spectroscopic analysis prior to catching revealed the presence of olivine phenocrysts, pyroxene groundmass, and plagioclase feldspar assemblages, typical of tholeiitic basalts that form through partial melting of ultramafic mantle compositions under low-pressure conditions. These mineralogical associations suggest eruption from fissure systems rather than central volcanic vents, indicating that early Martian volcanism operated through flood basalt mechanisms similar to those that created Earth's largest igneous provinces during mass extinction events. The sample preserves primary igneous textures despite billions of years of exposure to cosmic radiation, thermal cycling, and chemical weathering processes that gradually alter rock surfaces throughout geological time. The caching process requires precise robotic manipulation as mechanical systems transfer the sample tube from the drill assembly to the rover's belly-mounted storage carousel, where it joins other collected specimens awaiting eventual retrieval by future Mars sample return missions. This sample handling operation occurs in the open Martian environment where dust particles and atmospheric gases could potentially contaminate pristine rock surfaces, necessitating careful timing and protective procedures that minimize exposure to external contaminants. The transfer mechanisms operate through sterilized pathways and controlled atmospheres that preserve sample integrity while accommodating the mechanical constraints imposed by operating robotic systems at temperatures approaching absolute zero during Martian winter nights. Each cached sample undergoes detailed photographic documentation that records its orientation, surface textures, and contextual relationships to surrounding rock formations, providing essential geological information that will guide laboratory analyses when the specimens eventually reach terrestrial facilities. These images capture millimeter-scale features that preserve evidence of crystallization environments, post-formation alteration processes, and potentially biological activity if microbial life ever colonized ancient Martian volcanic systems. The photographic record establishes provenance chains that connect individual rock samples to specific geological units, formation processes, and environmental conditions inferred from orbital reconnaissance and surface exploration data. The titanium storage tube contains headspace gases that represent atmospheric samples collected simultaneously with the solid rock specimen, preserving isotopic compositions and trace gas concentrations that reflect current Martian atmospheric chemistry. These gas samples provide opportunities for measuring noble gas isotope ratios, carbon dioxide compositions, and potential organic volatile compounds that escape detection by rover-mounted analytical systems. The atmospheric preservation aspect of sample caching transforms each geological specimen into a combined solid gas sample that doubles the scientific return from individual collection operations while providing constraints on volatile cycling and atmospheric evolution processes. Thermal monitoring systems track temperature conditions throughout the caching sequence, ensuring that sample preservation occurs within acceptable ranges that prevent thermal decomposition of organic compounds or phase transitions that could alter mineral structures and chemical compositions. The monitoring data reveals how Martian diurnal temperature cycles affect sample storage conditions and mechanical system performance, providing engineering information essential for designing future sample return missions that must maintain specimen integrity during complex orbital mechanics and atmospheric entry procedures. These thermal constraints require sophisticated engineering solutions that balance sample preservation requirements against mass limitations and power consumption restrictions inherent in interplanetary mission design. The cached sample represents approximately 0.0000000% of Mars's total mass. Yet, this infinitesimal fraction contains information that could revolutionize understanding of planetary formation, early life emergence, and habitability potential throughout the solar system. Laboratory analysis of the returned specimens will employ analytical techniques unavailable on rover platforms, high-resolution mass spectrometry, electron microprobe analysis, and synchrotron X-ray tomography that can detect biosignatures at concentrations measured in parts per billion while preserving spatial context and mineralogical associations. These capabilities exceed rover instrument sensitivity by factors of 10,000 or more, transforming returned samples into comprehensive geological archives that preserve multiple lines of evidence for ancient environmental conditions. The sample catching operation concludes with digital documentation that records collection coordinates, geological context, analytical results from rover instruments, and environmental conditions during the acquisition sequence. This metadata accompanies each specimen throughout its eventual journey to Earth, providing essential information for laboratory investigators who will analyze the samples using techniques not yet invented and research questions not yet formulated. The documentation process creates permanent records that link individual rock specimens to specific locations within Jezero craters' geological formations, enabling future researchers to reconstruct ancient environmental conditions with unprecedented spatial and temporal resolution. Storage carousel mechanisms rotate the newly cached sample into position alongside previously collected specimens, creating a growing archive of Martian geological materials that represents humanity's first systematic sampling of another planet's geological record. The carousel design accommodates multiple sample types: igneous rocks, sedimentary formations, potential biosignature targets, and atmospheric gas samples, while maintaining individual container integrity and preventing cross-contamination between specimens collected from different geological units. Only took 50 years of planetary exploration to develop sample collection and preservation technologies capable of maintaining specimen integrity during decade-long storage periods under extraterrestrial environmental conditions. The rover's analytical instruments converge upon olivine crystals that preserve memories of primordial Martian magma chambers, their emerald green compositions recording temperatures and pressures that existed when the planet's molten interior generated volcanic activity rivaling Earth's most productive igneous provinces. These iron-magnesium silicate minerals crystallized at depths approaching 50 kilometers beneath Mars's ancient surface, where convecting mantle plumes delivered heat and chemical components from core mantle boundary regions that operated under thermodynamic conditions similar to those maintaining Earth's ongoing plate tectonics. PIXL's X-ray spectrometer reveals forsterite compositions with magnesium numbers, indicating equilibrium with primitive basaltic melts, suggesting that early Martian volcanism tapped directly into undifferentiated mantle sources without the crustal contamination processes that characterize more evolved planetary volcanic systems. The olivine phenocrysts appear as elongated crystals measuring several millimeters in length, their euhedral faces preserving original growth morphologies despite billions of years of exposure to cosmic radiation and chemical weathering processes that gradually alter mineral surfaces through atomic displacement and oxidation reactions. Mahalai's close-up photography reveals crystallographic features invisible to orbital reconnaissance. The subtle zonation patterns where magnesium and iron concentrations varied during progressive crystallization. The inclusion trails where immiscible sulfide droplets became trapped within growing crystal lattices, and the dissolution textures where subsequent magma reheating partially resorbed earlier formed mineral phases. These petrographic details record complex thermal histories as magma chambers underwent cooling, reheating, and compositional evolution through processes that operated over timescales measured in thousands to millions of years. SuperCam's laser spectroscopy penetrates beneath weathered olivine surfaces to reveal pristine mineral compositions that escaped alteration by atmospheric chemistry and surface oxidation processes, detecting nickel concentrations that indicate equilibrium with metallic iron phases during core formation and early planetary differentiation. The trace element signatures suggest that Martian olivine crystallized from magmas with sulfur abundances exceeding those typical of terrestrial basalts, reflecting core formation processes that operated under more reducing conditions than those characterizing Earth's early evolution. These geochemical differences provide insights into planetary accretion mechanisms and volatile inventory variations that influenced habitability potential during the first billion years of solar system history. The olivine crystals exhibit alteration rinds where interaction with aqueous solutions transformed original silicate compositions into secondary mineral assemblages that require liquid water for their formation and stability. These alteration products include serpentine minerals with characteristic plated structures, Idding site formations with distinctive orange coloration, and clay mineral developments that preserve isotopic signatures of ancient water-rock interaction processes. The transition zones between fresh olivine cores and altered margins record progressive degrees of hydration and oxidation that occurred as groundwater circulated through fractured volcanic rocks during periods when Mars maintained atmospheric pressures sufficient for liquid water stability. Spectroscopic analysis reveals that the olivine alteration occurred under alkaline conditions with pH values approaching 9 or 10, similar to terrestrial serpentinization environments where ultramafic rocks interact with carbonate-rich groundwater to produce hydrogen gas and methane through abiotic synthesis pathways. These chemical conditions create energy sources that support chemosynthetic microbial communities in Earth's deep subsurface and oceanic hydrothermal systems, suggesting that similar environments on early Mars might have provided habitable niches for extremophile organisms if life ever emerged on the planet. The alteration mineralogy indicates water temperatures between 50 and 100 degrees Celsius, optimal for biological activity and organic compound preservation under conditions that persisted for millions of years. The rover's instruments detect chromium spinel inclusions within olivine crystals, microscopic mineral phases that crystallized at even higher temperatures and provide constraints on mantle source compositions and partial melting processes that generated the parent magmas. These accessory minerals contain platinum group elements and rare earth element patterns that indicate derivation from primitive mantle compositions similar to those inferred for Earth's Archean mantle before extensive crustal recycling and contamination modified the planet's interior chemistry. The spinel composition suggests that early Martian volcanism accessed mantle source regions with elevated aluminum and chromium concentrations, reflecting planetary differentiation processes that operated differently from those characterizing terrestrial mantle evolution. Crystallographic analysis through detailed optical microscopy reveals that some olivine crystals preserve shock features characteristic of high-pressure deformation during meteorite impact events, including planar deformation features, melt inclusions, and crystal lattice dislocations that formed when asteroid impacts generated pressures exceeding 10 gigapascals throughout volumes of crustal rock. These shock textures indicate that the olivine-bearing volcanic rocks experienced subsequent modification during the late heavy bombardment when massive impact events repeatedly fractured and heated Mars' upper crust to depths approaching several kilometers. The preservation of both primary igneous textures and secondary shock features provides insights into the timing relationships between volcanic activity and impact bombardment during Mars's early geological evolution. Temperature estimates based on olivine pyroxene geothermometry indicate crystallization temperatures approaching 1200 degrees Celsius, confirming that the parent magmas were sufficiently hot to remain fluid during transport from mantle source regions to surface eruption sites without extensive cooling and crystallization en route. These high temperatures suggest rapid magma ascent through relatively simple plumbing systems, rather than the complex crustal magma chamber networks that characterize terrestrial volcanic systems with extended residence times and opportunities for compositional evolution through fractional crystallization processes. The thermal constraints indicate that early Martian volcanism operated through efficient heat transfer mechanisms that delivered primitive mantle compositions directly to the planet's surface. Trace element analysis reveals that the olivine crystals contain elevated concentrations of lithium, beryllium, and boron that might indicate interaction with hydrothermal fluids enriched in these light elements through leaching of altered crustal rocks or evaporate deposits. These trace element signatures could represent evidence of extensive fluid circulation systems that operated during the transition from volcanic activity to impact bombardment, when fracture networks created pathways for deep groundwater circulation and chemical exchange between surface and subsurface reservoirs. The elevated light element concentrations might also indicate atmospheric volatile cycling processes that concentrated these components in surface and near-surface environments through evaporation and precipitation mechanisms. The olivine preservation within volcanic rocks that erupted. 6 billion years ago demonstrates remarkable chemical stability despite exposure to oxidizing atmospheric conditions and cosmic radiation fluxes that would decompose most organic compounds within geological timescales measured in millions rather than billions of years. This mineral stability indicates that Mars's surface environment, while hostile to biological activity, nonetheless preserves geological records with fidelity sufficient for reconstructing ancient environmental conditions and potentially detecting biosignatures if they ever formed in more clement periods of planetary history. Only took 4 billion years for these olivine crystals to travel from Mars's mantle to robotic analysis under alien skies, preserving atomic-scale information about processes that operated when Earth was still a molten planet without continents, oceans, or any trace of life. The sedimentary layers unfold like pages in an ancient manuscript, each stratum preserving a chapter from Mars's hydrological history when rivers carved channels through highland terrain and deposited clay-rich sediments in standing water bodies that persisted for millions of years. These stratified deposits rise from Jazero's crater floor in ordered succession, their horizontal bedding planes recording episodic deposition events separated by periods of erosion, exposure, and chemical alteration that created unconformable contacts between distinct sedimentary packages. Mahali's close-up photography reveals the intimate details of these depositional sequences. The graded bedding where grain sizes decrease upward within individual layers. The cross-stratification that indicates current directions and flow velocities. And the mudstone interbeds that accumulated during quiescent periods when suspended particles settled from still water columns under conditions of minimal turbulence. Each sedimentary layer represents a discrete environmental snapshot that captures atmospheric conditions, water chemistry, and sediment transport processes operating when Mars possessed climatic stability sufficient for sustained fluvial activity. The lowermost strata contain coarse-grained conglomerates with rounded clasts that traveled hundreds of kilometers from highland source regions, their smooth surfaces recording abrasion processes during extended transport in high-energy river systems that carved deep valleys through ancient impact crater rims. These basal deposits grade upward into sandstone layers with well-sorted grain sizes that indicate more mature sedimentary systems where repeated reworking concentrated quartz and feldspar fragments while removing unstable mineral phases through chemical weathering and mechanical attrition. PIXL's elemental analysis reveals systematic compositional variations between adjacent sedimentary layers, detecting iron oxide concentrations that fluctuate with depositional environment and redox conditions in ancient water bodies that experienced seasonal or longer-term changes in oxygenation levels. The uppermost fine-grained layers contain elevated aluminum and silicon abundances characteristic of clay mineral accumulation, while intermediate zones show calcium and sulfur enrichments that indicate evaporate formation during periods of restricted water circulation and enhanced evaporation rates. These geochemical signatures record transitions between open lacustrine conditions and closed basin environments where concentrated brines precipitated mineral salts similar to those forming in terrestrial alkaline lakes and playa systems. The sedimentary architecture preserves evidence of multiple transgressive regressive cycles where lake levels rose and fell in response to climatic variations driven by orbital mechanics, volcanic outgassing, and atmospheric evolution processes that modified precipitation patterns and evaporation rates over timescales measured in thousands to millions of years. Rising water levels created deeper depositional environments where fine-grained sediments accumulated in quiet water conditions, while falling lake levels exposed previously submerged areas to erosion and produced unconformities that separate distinct sedimentary packages. These cyclical patterns mirror terrestrial lacustrine sequences, yet preserve unique signatures of environmental conditions that have no modern analogues on Earth. SuperCam's laser spectroscopy penetrates weathered surfaces to reveal pristine mineral compositions within individual sedimentary layers, detecting phyllosilicate abundances that require extended water-rock interaction under alkaline conditions favoring clay mineral formation and stability. The spectroscopic data indicates that these sedimentary deposits contain multiple clay mineral species, montmorillonite, formed through volcanic ash alteration, kaolinite produced by feldspar weathering under acidic conditions, and chlorite developed through hydrothermal alteration of mafic mineral assemblages. This clay mineral diversity suggests complex fluid chemistry evolution as ancient Martian surface waters interacted with different rock types and experienced pH variations that favored different alteration pathways and secondary mineral formation processes. Detailed sedimentological analysis reveals current ripple structures preserved on individual bedding surfaces, their asymmetric morphologies indicating paleocurrent directions that flowed consistently from northwest to southeast across Jezero's ancient delta system. These sedimentary structures formed when flowing water transported sand-sized particles across the lake floor, creating bed forms that migrated downstream while preserving directional information about ancient river systems that drained highland watersheds covering thousands of square kilometers. The ripple orientations provide quantitative constraints on paleogeographic reconstructions that connect Jezero's lacustrine deposits to specific source regions where erosion and weathering processes generated the sediments now preserved in stratified sequences. The rover's stereo imaging capabilities generate three-dimensional models of sedimentary outcrop faces that reveal subtle depositional features invisible in two-dimensional photographs, including channel fill sequences where meandering rivers carved and filled abandoned course, point bar deposits that accumulated on the inside bends of sinuous channels, and overbank sediments that spread across floodplains during high discharge events. These architectural elements record fluvial system evolution as river channels migrated laterally across the landscape while simultaneously aggrading vertically through continued sediment supply from highland source regions experiencing active erosion and chemical weathering processes. Trace fossil analysis focuses on laminated sedimentary structures that might preserve evidence of microbial mat formation in shallow water environments where photosynthetic or chemosynthetic organisms could have thrived under early Martian atmospheric conditions. These potential biosignatures require careful documentation and eventual laboratory analysis to distinguish between biogenic lamination and abiotic sedimentary processes that can produce remarkably similar textures through purely physical and chemical mechanisms. The preservation potential for organic signatures in clay-rich sediments exceeds that of most other geological environments, making these stratified deposits prime targets for astrobiological investigations that seek evidence of ancient life on Mars. Mineralogical analysis reveals that some sedimentary layers contain carbonate minerals that precipitated from alkaline lake waters under atmospheric carbon dioxide, partial pressures that might have differed significantly from modern Martian atmospheric compositions. These carbonate deposits indicate that ancient surface waters achieved chemical conditions capable of sequestering atmospheric carbon dioxide through mineral precipitation processes that operated when Mars possessed denser atmospheric envelopes and possibly active carbon cycling between atmospheric, hydrological, and geological reservoirs. The carbonate mineralogy provides constraints on ancient atmospheric compositions and greenhouse gas concentrations that influenced planetary climate evolution during the transition from early warm and wet conditions to to current cold and dry environmental states. The sedimentary record preserves evidence of catastrophic flooding events when dam failures or volcanic outbursts released massive volumes of stored water that carved channels and deposited distinctive sedimentary signatures throughout Jezero's drainage basin. These mega-flood deposits contain exotic clasts transported from distant source regions, impact breccias that record continued bombardment during lacustrine deposition, and volcanic ash layers that provide temporal markers for correlating sedimentary sequences with igneous activity recorded in orbital geological mapping studies. The flood deposits represent some of the youngest aqueous activity preserved in Jezero's sedimentary archive, recording environmental conditions that persisted until relatively late in Mars's geological evolution, when liquid water became increasingly unstable under evolving atmospheric and climatic conditions. Only took 4 billion years for these sedimentary layers to transition from active underwater deposition to freeze-dried preservation in the Martian desert, maintaining textural and compositional information that rivals the best-preserved terrestrial stratigraphic sections despite exposure to cosmic radiation and oxidizing surface chemistry that would degrade most organic compounds and unstable mineral phases within geological timescales measured in millions of years rather than billions. Spectroscopic whispers reveal the presence of organic molecules embedded within billion-year-old mudstone. Their carbon-based signatures, detected through analytical techniques that distinguish between indigenous Martian chemistry and potential contamination from terrestrial sources or meteoritic delivery during the late heavy bombardment. SuperCam's laser spectroscopy identifies aromatic hydrocarbon compounds preserved within clay mineral matrices that protected these fragile molecules from cosmic radiation and oxidizing surface chemistry through geological timescales that witnessed the rise and fall of entire biological kingdoms on Earth. The organic signatures appear as subtle spectral features that require sophisticated data processing algorithms to extract from background noise and interference patterns. Yet their detection represents a profound scientific achievement that transforms understanding of Mars's chemical evolution and potential for ancient biological activity. The mudstone host rock, formed in quiet lacustrine environments where fine-grained sediments accumulated slowly enough to preserve delicate organic structures without the mechanical disruption that characterizes higher-energy depositional systems. These depositional conditions favored the concentration and preservation of carbon compounds through adsorption onto clay mineral surfaces, incorporation into evaporate crystals, and burial beneath protective sedimentary layers that prevented photochemical decomposition and thermal degradation. The organic molecules survived billions of years of exposure to temperature cycling, impact bombardment, and atmospheric chemistry variations that would decompose most biological materials within thousands of years under modern Martian surface conditions. Chemical analysis reveals a diverse suite of organic compounds, including thiophenies, benzene derivatives, and chlorinated hydrocarbons that could represent either biological synthesis pathways or abiotic formation processes operating in ancient hydrothermal systems where organic chemistry occurs through metal catalysis and thermochemical reactions. The molecular complexity exceeds that expected from simple abiotic synthesis, yet remains consistent with both biological production and sophisticated geochemical processes that operate in terrestrial hydrothermal environments, where organic compounds form through serpentinization reactions and Fischer-Tropsch synthesis pathways. This ambiguity represents one of the most intriguing scientific mysteries presented by Mars exploration, requiring eventual sample return and laboratory analysis to resolve definitively. The organic compounds occur in spatial association with sulfur-bearing minerals that indicate reducing environmental conditions, favoring organic preservation, and potentially supporting chemosynthetic metabolic pathways that utilize sulfur compounds as energy sources for biological activity. These sulfur signatures suggest that ancient Martian groundwater systems possessed chemical characteristics similar to terrestrial environments, where extremophile microorganisms thrive in the absence of photosynthetic primary production, deriving energy from inorganic chemical reactions rather than solar radiation. The co-occurrence of organic molecules and sulfur minerals provides circumstantial evidence for ancient biochemical processes, though alternative explanations involving purely geochemical formation mechanisms remain plausible. PIXL's high-resolution elemental mapping reveals that organic carbon concentrations vary systematically with sedimentary texture and mineralogy, showing elevated abundances in fine-grained layers where clay minerals and organic matter co-precipitated from ancient lake waters under conditions that favored both clay formation and organic preservation. The spatial distribution patterns suggest that organic accumulation occurred through normal sedimentary processes rather than post-depositional migration or contamination events that would produce different concentration patterns and mineralogical associations. These observations support indigenous formation or deposition of organic compounds during active lacustrine sedimentation, when Jezero crater contained standing water for extended periods. Isotopic analysis through advanced mass spectrometry techniques reveals carbon isotope ratios that fall within ranges characteristic of biological fractionation processes, though overlapping with values expected from abiotic organic synthesis under specific temperature and chemical conditions. The carbon-13 to carbon-12 ratios indicate preferential incorporation of lighter isotopes that could represent either metabolic fractionation by ancient microorganisms or kinetic isotope effects during thermochemical organic formation in hydrothermal systems. The isotopic signatures provide additional evidence for biological processes while remaining consistent with alternative formation mechanisms that complicate definitive interpretation without additional analytical constraints from returned sample analysis. The preservation of organic molecules within Martian sedimentary rocks demonstrates that carbon-based chemistry can survive geological timescales under extraterrestrial environmental conditions, providing encouragement for astrobiological investigations throughout the solar system where similar preservation mechanisms might operate. Clay mineral matrices serve as natural preservation media that protect organic compounds from radiation damage, thermal decomposition, and chemical oxidation through adsorption processes and structural incorporation that create stable organic mineral associations. These preservation mechanisms operate independently of biological origin, suggesting that organic signatures from ancient life or abiotic synthesis could persist for billions of years if deposited under appropriate geological conditions. Spectroscopic analysis identifies organic sulfur compounds that represent either biological sulfur cycling processes or thermochemical reactions between organic matter and sulfur-bearing minerals during diagenetic alteration of sedimentary deposits. These organosulfur molecules form readily in both biological and abiotic systems, yet their specific molecular structures and isotopic compositions might preserve diagnostic information about formation mechanisms that distinguish between biological and geochemical origins. The detection of complex organic sulfur chemistry expands the known inventory of Martian organic compounds, while highlighting the sophisticated chemical processes that operated in ancient surface environments. The organic compounds occur within sedimentary layers that also contain evidence of ancient microbial structures, including laminated textures reminiscent of terrestrial stromatolites, spherical features that resemble fossilized microorganisms, and mineral precipitates with morphologies similar to those produced by bacterial metabolic processes. These potential biosignatures require extremely careful analysis to distinguish between authentic biological structures and abiotic mimics that can form through purely geochemical processes operating under specific environmental conditions. The co-occurrence of organic molecules and potential microbial structures strengthens the case for ancient biological activity while remaining consistent with complex abiotic processes that deserve equally serious scientific consideration. Laboratory analysis of returned samples will employ analytical techniques unavailable on rover platforms, including two-dimensional gas chromatography, high-resolution mass spectrometry, and molecular structural analysis that can identify specific organic compounds and distinguish between biological and abiotic formation pathways through detailed molecular fingerprinting. These advanced analytical capabilities will determine whether the detected organic signatures represent indigenous Martian biochemistry, abiotic synthesis in ancient hydrothermal systems, or delivery from external sources during meteorite bombardment events that brought organic compounds from asteroids, comets, or even other planetary bodies throughout the solar system. Only took 50 years of planetary exploration and analytical chemistry development to achieve sufficient sensitivity and selectivity for detecting organic molecules preserved in ancient Martian sedimentary rocks, transforming the search for life from philosophical speculation into quantitative scientific investigation through robotic proxies operating millions of kilometers from their human controllers, yet capable of performing analytical procedures that rival terrestrial laboratory capabilities. The chemistry of lost rivers emerges through hydrated mineral signatures that map ancient water pathways carved through Jezero's crater rim when liquid streams cascaded from highland watersheds into the standing lake that once filled this 45-kilometer basin. PIXL's elemental analysis reveals calcium sulfate deposits concentrated along former channel margins where evaporating water precipitated gypsum crystals during seasonal dry periods or longer-term climatic transitions toward increasingly arid conditions. These evaporate minerals preserve isotopic signatures of ancient surface waters that flowed when Mars possessed atmospheric pressure sufficient to maintain liquid stability, and perhaps even weather patterns that delivered precipitation to highland catchments through mechanisms similar to terrestrial hydrological cycling. The rover traces mineral assemblages that record progressive chemical evolution as river waters interacted with diverse rock types during transport from volcanic source regions to lacustrine depositional environments hundreds of kilometers downstream. Iron-bearing phyllosilicates mark zones where flowing water leached cations from basaltic bedrock and precipitated clay minerals under alkaline conditions that favored serpentine and smectite formation over the acidic alteration products that characterize sulfur-rich environments. These clay mineral distributions create chemical maps of ancient drainage networks that carried dissolved ions and suspended sediments across landscapes that experienced active erosion and chemical weathering processes operating under climatic conditions fundamentally different from modern Mars. SuperCam's laser spectroscopy penetrates through surface dust to reveal hydrated silica deposits that formed where hot springs discharged silica-rich groundwater into river channels, creating opaline precipitates, similar to those found in terrestrial geothermal systems where subsurface heating drives extensive water-rock interaction and mineral dissolution processes. The silica deposits contain fluid inclusion arrays that trapped samples of ancient Martian groundwater within crystalline matrices, preserving chemical compositions and possibly even microbial remains if thermophilic organisms colonize these hydrothermal environments when temperatures and chemical conditions supported biological activity. These fossil hot springs represent some of the most promising targets for detecting preserved biosignatures on Mars. Trace element analysis reveals systematic downstream variations in water chemistry as ancient rivers dissolved different mineral phases and concentrated specific ions through evaporation, precipitation, and ion exchange processes that operated during extended transport through varied geological terrains. Lithium concentrations increased toward the crater center, where focused evaporation concentrated this highly soluble element in terminal lake deposits. while strontium abundances reflect feldspar weathering in highland watersheds and subsequent carbonate precipitation under alkaline lacustrine conditions. These chemical gradients preserve quantitative information about ancient water flow rates, residence times, and seasonal variations that influenced mineral saturation states and precipitation sequences. The hydrated mineral assemblages indicate that ancient Martian surface waters achieved neutral to alkaline pH values through interaction with olivine-rich volcanic rocks that buffered acidity and created chemical conditions favorable for clay mineral formation and organic preservation. This alkaline chemistry contrasts sharply with the acidic conditions inferred for younger Martian aqueous environments dominated by sulfur-rich mineral assemblages formed during later periods when volcanic outgassing and atmospheric evolution shifted surface water chemistry toward increasingly corrosive compositions. The temporal progression from alkaline to acidic conditions records fundamental changes in planetary volcanism, atmospheric evolution, and surface chemistry that influenced habitability potential throughout Mars's geological history. Detailed mineralogical mapping reveals channel-filled deposits where meandering rivers carved and subsequently abandoned former courses, leaving behind sedimentary sequences that preserve lateral migration patterns and temporal changes in discharge patterns over thousands of years. These paleochannel deposits contain the highest concentrations of hydrated minerals and organic signatures detected within Jezero crater, suggesting that flowing water environments provided optimal conditions for concentrating and preserving chemical evidence of ancient environmental conditions and potentially biological activity. The channel fill sequences represent natural sediment traps that accumulated organic matter, clay minerals, and trace elements during extended periods of fluvial activity. Spectroscopic analysis identifies zeolite minerals within altered volcanic ash layers that record interaction between airborne pyroclastic deposits and surface waters during periods when active volcanism supplied both heat sources for hydrothermal circulation and chemical components for extensive water-rock interaction processes. These zeolites form only under specific temperature, pressure, and chemical conditions that require sustained hydrothermal activity over time scales measured in thousands to millions of years, indicating that early Martian groundwater systems possessed sufficient thermal energy and chemical reactivity to support complex mineral alteration processes. The zeolite assemblages suggest that subsurface temperatures reached 100 to 200 degrees Celsius, optimal for organic synthesis and potentially biological activity in hydrothermal environments. The river chemistry indicators extend beyond Jezero's immediate vicinity through orbital mineral mapping that connects local hydrated mineral signatures to regional geological formations spanning thousands of square kilometers across Martian highland terrain. These regional connections demonstrate that the aqueous processes recorded in Jezero's sedimentary deposits represent parts of much larger hydrological systems that operated when Mars maintained global climate conditions capable of supporting extensive surface water networks. The scale of these ancient river systems rivals terrestrial watersheds and indicates planetary water inventories sufficient to sustain active hydrological cycling for millions of years. Geochemical modeling based on observed mineral assemblages suggests that ancient Martian surface waters contained dissolved carbon dioxide concentrations that maintained carbonic acid buffering systems similar to those operating in terrestrial groundwater environments, creating chemical conditions that could support carbonate precipitation and possibly biological carbon fixation processes. The modeled water compositions indicate moderate salinity levels and trace element concentrations within ranges that support microbial life in terrestrial analog environments, strengthening the case for potential habitability in ancient Martian aqueous systems while highlighting the sophisticated geochemical processes that operated during the planet's more clement early history. The preservation of hydrated mineral assemblages through billions of years of cosmic radiation exposure and temperature cycling demonstrates remarkable chemical stability under Martian surface conditions, suggesting that these materials could preserve even more delicate signatures of ancient environmental conditions and biological activity if such evidence exists within the geological record. Laboratory analysis of return samples will reveal detailed molecular structures and isotopic compositions of hydrated minerals that provide quantitative constraints on ancient water temperatures, chemical compositions, and residence times that influenced mineral formation and potentially biological processes in early Martian surface environments. Only took 30 years of orbital mineral mapping and surface exploration to reconstruct the chemical evolution of river systems that ceased flowing billions of years before complex life emerged on Earth, demonstrating how geological materials preserve detailed records of planetary environmental conditions across timescales that encompass the entire history of biological evolution in the solar system. Seasonal methane mysteries emerge from atmospheric monitoring as Perseverance's sensors detect trace concentrations of this simple hydrocarbon that fluctuate with Mars's orbital mechanics and regional atmospheric circulation patterns that redistribute gases across hemispheric scales. The tunable laser spectrometer operates through infrared absorption techniques that identify specific molecular vibrations characteristic of methane's carbon-hydrogen bonds, achieving sensitivity levels approaching parts per billion despite the overwhelming abundance of carbon dioxide that dominates Martian atmospheric composition. These methane detections occur sporadically and at concentrations barely above instrumental detection limits, creating one of the most perplexing scientific mysteries in planetary atmospheric chemistry, where trace gas behavior challenges conventional understanding of photochemical processes and atmospheric lifetime calculations. The seasonal variations follow patterns that correlate weakly with Martian spring and summer, when increased solar heating enhances atmospheric mixing and potentially releases methane from subsurface reservoirs, where the gas might accumulate through geological or biological production processes. Peak concentrations appear during late southern summer, when atmospheric pressure reaches annual maxima, and global dust storms redistribute atmospheric constituents through convective processes that transport trace gases from their source regions to detection sites hundreds of kilometers away. These temporal patterns suggest that methane sources operate continuously at low levels rather than through episodic releases. Yet the gas disappears from atmospheric measurements faster than photochemical models predict for destruction by hydroxyl radicals and atomic oxygen species generated by ultraviolet radiation. The rover's atmospheric measurements reveal methane abundance variations that occur over timescales ranging from hours to seasons, indicating complex source and sink processes that operate under environmental conditions unique to Mars' thin atmosphere and oxidizing surface chemistry. Diurnal variations show subtle increases during pre-dawn hours when atmospheric mixing reaches daily minima and surface cooling creates temperature inversions that could concentrate trace gases near ground level, where the rover's sensors achieve maximum sensitivity. These short-term fluctuations might reflect local methane emissions from subsurface sources or atmospheric transport processes that concentrate the gas through meteorological mechanisms operating within Jezero crater's topographic basin. Isotopic analysis through high-resolution spectroscopy attempts to distinguish between geological and biological methane sources by measuring carbon-13 to carbon-12 ratios that differ significantly between thermogenic production in subsurface environments and biogenic formation through microbial metabolic processes. The spectroscopic measurements approach the limits of instrumental precision and require extensive atmospheric sampling over multiple Martian seasons to accumulate sufficient data for statistically significant isotopic determinations. Preliminary results suggest carbon isotope ratios consistent with either geological formation through serpentinization reactions or biological production by methanogenic RKE. Maintaining the ambiguity that characterizes most potential biosignatures detected on Mars, the methane detection sensitivity varies with atmospheric conditions, including dust loading, temperature profiles, and pressure variations that affect instrumental performance and atmospheric optical properties throughout the Martian year. Global dust storms temporarily degrade measurement precision by scattering infrared radiation and altering atmospheric temperature structure, while seasonal pressure cycles change the collision broadening of spectral lines that influences peak shapes and absorption intensities. These environmental factors require sophisticated calibration procedures and data correction algorithms that account for changing atmospheric conditions while maintaining sensitivity to genuine methane variations that might indicate active source processes. Spatial analysis reveals that methane detections cluster around specific geological features, including impact crater centers, volcanic calderas, and sedimentary basin margins where subsurface structures might provide pathways for gas migration from deep reservoirs to atmospheric release points. These spatial correlations suggest geological control of methane emissions through fracture networks, permeable sedimentary layers, or hydrothermal circulation systems that transport gases from source regions to surface expression sites. The geological associations strengthen arguments for abiotic methane production through water-rock interactions in subsurface environments where serpentinization processes generate hydrogen and methane under reducing conditions. Laboratory experiments demonstrate that methane formation occurs readily through serpentinization of olivine-rich rocks under hydrothermal conditions similar to those inferred for Mars's subsurface environment, where liquid water might persist in deep aquifer systems despite surface conditions hostile to water stability. These experimental results indicate that geological methane production requires only water, carbon dioxide, and ultramafic rock compositions that exist abundantly throughout Mars's crust, suggesting that abiotic methane generation could operate continuously through geological processes that do not require biological activity. The experimental work provides plausible mechanisms for methane formation while highlighting the difficulty of distinguishing between geological and biological sources based solely on atmospheric measurements. Atmospheric modeling studies attempt to reconcile observed methane concentrations with photochemical destruction rates calculated from laboratory measurements of reaction kinetics and Martian atmospheric compositions. Yet these models consistently predict atmospheric lifetimes much shorter than required to explain observed spatial and temporal variations. The modeling discrepancies suggest either unknown atmospheric chemistry processes that protect methane from rapid destruction or subsurface reservoirs that continuously replenish atmospheric concentrations through sustained emission processes. These theoretical challenges highlight fundamental gaps in understanding Martian atmospheric chemistry and the complex interactions between surface, subsurface, and atmospheric processes. The methane mystery extends beyond Mars to encompass broader questions about trace gas cycling in planetary atmospheres, where oxidizing surface chemistry and thin atmospheric envelopes create conditions unlike those found on Earth or other solar system bodies. Comparative planetology suggests that methane detection on Mars represents a unique phenomenon that provides insights into atmospheric evolution processes and potentially biological activity under environmental conditions that push the boundaries of known habitability limits. The trace gas measurements transform understanding of Mars from a geologically inactive planet to a world where active processes continue to operate billions of years after major geological and climatic transitions. Future methane investigations will employ more sensitive analytical techniques and expanded spatial coverage through orbital measurements that complement surface observations with global-scale monitoring capabilities, potentially identifying source regions and seasonal patterns that explain the mysterious temporal and spatial variations detected by rover-based atmospheric sensors. The combined surface and orbital datasets will provide constraints on methane production mechanisms, transport processes, and destruction pathways that determine trace gas cycling in Martian atmospheric systems, where chemical processes operate under conditions unlike any terrestrial analogs. Only took 20 years of increasingly sophisticated atmospheric monitoring to detect methane on Mars at concentrations that challenge instrumental capabilities, yet provide tantalizing evidence for active processes that might include biological activity. Transforming the search for life from geological investigations to atmospheric chemistry studies that explore the boundary between geochemistry and biochemistry in planetary environments. The sample depot emerges across a carefully selected patch of Martian regolith, where Perseverance methodically places sealed titanium tubes like metallic seeds awaiting future harvest by spacecraft that exist only in engineering drawings and mission planning documents. Each cache site undergoes thorough photographic documentation and geological characterization to ensure that sample tubes remain accessible to retrieval systems while maintaining their hermetic seals and internal atmospheric conditions throughout the months or years required for Mars sample return mission development, launch, and interplanetary transit. The depot creation process transforms Jezero Crater into humanity's first extraterrestrial warehouse, where geological specimens worth billions of dollars in mission development costs rest beneath alien skies, while engineers on Earth refine technologies for the most complex robotic operation ever attempted. The rover positions each sample tube with centimeter-level precision using robotic arm capabilities that surpass human dexterity in environments where protective suits would prevent fine motor control and atmospheric conditions would prove immediately lethal to unprotected explorers. GPS navigation systems operate through triangulation with orbital relay satellites that maintain communication links across interplanetary distances, while accounting for relativistic effects and signal propagation delays that complicate real-time robotic control from Earth-based mission operations centers. The placement procedure requires multiple sols of careful maneuvering as engineers verify tube orientation, stability, and accessibility before confirming successful depot operations and updating spacecraft navigation databases with precise coordinate information. Each cached sample represents specific geological formations and environmental conditions that guided the rover's traverse planning and scientific target selection throughout its extended mission in Jezero Crater's sedimentary and igneous formations. The depot contains igneous rocks from ancient volcanic episodes, sedimentary specimens from lacustrine deposition environments, altered materials from hydrothermal systems, and atmospheric gas samples that preserve chemical signatures of current Martian atmospheric compositions. This diverse sample suite provides comprehensive representation of geological processes that operated throughout Mars' 5 billion-year history while maximizing scientific return from eventual laboratory analysis using analytical techniques unavailable on rover platforms. The sample tubes undergo final inspection and sealing procedures that ensure contamination prevention and atmospheric preservation throughout extended exposure to Martian surface conditions, including temperature cycling, dust accumulation, and cosmic radiation bombardment that continues unabated in the absence of protective atmospheric shielding. Each titanium container maintains internal pressure and gas composition through hermetic seals, tested to withstand temperature variations exceeding 100 degrees Celsius and mechanical stresses equivalent to spacecraft launch and atmospheric entry procedures. The sealing technology represents decades of materials science development focused on preserving extraterrestrial samples under conditions more extreme than any terrestrial storage environment. Detailed mapping protocols record the precise geographic coordinates, geological context, and sample characteristics for each depot location using coordinate systems that account for Mars's rotational dynamics, polar motion, and orbital mechanics that influence positional accuracy over the timescales required for sample return operations. The mapping data integrates with orbital reconnaissance imagery and geological surveys that provide regional context for understanding the broader significance of individual rock specimens within Mars's geological evolution and environmental history. These spatial datasets enable future missions to locate cached samples with accuracy approaching individual tube dimensions despite operating robotic systems across interplanetary distances. The depot creation strategy distributes cached samples across multiple locations to minimize mission risk and maximize retrieval opportunities for future spacecraft that must land precisely enough to collect specific titanium tubes from predetermined coordinates on an alien world. Redundant depot sites provide backup options if primary retrieval locations become inaccessible due to mechanical failures, adverse weather conditions, or unforeseen geological hazards that could compromise sample recovery operations. The distributed caching approach balances scientific objectives against engineering constraints while acknowledging the inherent risks involved in complex multi-mission sample return campaigns. Thermal monitoring systems track temperature conditions within cached samples to ensure preservation of volatile compounds and organic molecules that could degrade under extreme thermal cycling or prolonged exposure to temperatures approaching absolute zero during Martian winter nights. The thermal data provide constraints on sample preservation requirements for future missions that must maintain specimen integrity during collection, storage, launch, interplanetary transit, atmospheric entry, and terrestrial laboratory delivery operations spanning multiple years and involving temperature variations exceeding those experienced by any previous returned extraterrestrial materials. Each sample depot includes comprehensive metadata documentation that describes collection procedures, analytical results from rover instruments, geological context, and environmental conditions during sample acquisition and catching operations. This information accompanies cached specimens throughout their eventual journey to Earth laboratories, where researchers decades in the future will analyze materials using techniques not yet invented and address scientific questions not yet formulated. The metadata preservation ensures that future investigators understand the geological significance and analytical heritage of individual specimens, while providing essential context for interpreting laboratory results. The catching operations represent unprecedented international cooperation as multiple space agencies coordinate mission planning, technology development, and cost sharing for sample return campaigns that exceed the financial and technical capabilities of individual nations. European, American, and potentially other international partners contribute specialized technologies, including sample collection systems, orbital relay spacecraft, atmospheric entry vehicles, and terrestrial receiving facilities that collectively enable the most ambitious robotic exploration program ever attempted. The international collaboration demonstrates how scientific objectives transcend political boundaries when pursuing knowledge that benefits all humanity. Orbital reconnaissance spacecraft monitor depot locations using high-resolution cameras that document sample tube positions and environmental conditions throughout the extended storage period required for Mars sample return mission implementation. These orbital observations detect dust accumulation, tube displacement, and any environmental changes that might affect retrieval operations, while providing navigation references for future landing systems that must achieve precision approaching individual sample tube dimensions. The orbital monitoring ensures continuous awareness of depot status and sample accessibility throughout the multi-year development timeline. The sample depot creation concludes years of rover operations while initiating decades of anticipation as cached specimens await collection by spacecraft that represent humanity's next major step in planetary exploration and potentially the first definitive answer to questions about life beyond Earth. The titanium tubes rest in Martian regolith like time capsules that preserve chemical and geological information from a planet that might have supported biological activity billions of years ago, when Earth was still a volcanic world without continents, oceans, or any trace of the complex ecosystems that would eventually give rise to technological civilizations capable of exploring other worlds. Only took 60 years of space exploration to develop capabilities for collecting pristine geological specimens from another planet and caching them for eventual return to terrestrial laboratories, demonstrating how sustained scientific investment and international cooperation can achieve objectives that seemed impossible when humans first gazed at Mars through primitive telescopes and wondered whether the red planet might harbor life. Comparative planetology unfolds through each analytical measurement as Perseverance's instruments reveal fundamental similarities between Martian and terrestrial geological processes that operated under vastly different environmental conditions, yet followed identical physical laws governing mineral formation, sedimentary deposition, and chemical weathering throughout the solar system. The basaltic compositions detected in ancient Martian volcanic rocks match those found in Earth's oceanic crust and continental flood basalts, demonstrating that planetary differentiation processes generated similar igneous assemblages despite differences in planetary mass, core composition, and thermal evolution histories that influenced magma generation and volcanic activity patterns. These compositional parallels suggest that rocky planet formation follows predictable sequences where gravitational accretion, thermal differentiation, and crustal development operate through universal mechanisms that transcend individual planetary characteristics. The sedimentary structures preserved in Jazero's ancient lake deposits mirror those found in terrestrial lacustrine environments, where flowing water transported and deposited clastic materials according to hydrodynamic principles that remain constant throughout the universe, regardless of atmospheric pressure, gravitational acceleration, or water chemistry variations. Current ripples, cross-bedding patterns, and graded sequences record identical fluid flow processes operating on both planets. Yet the Martian examples formed under atmospheric conditions 10,000 times thinner than Earth's surface pressure and water chemistry dominated by dissolved salts that would prove toxic to most terrestrial organisms. This environmental divergence within similar depositional processes highlights how planetary atmospheres and surface chemistry evolution influence habitability, while geological processes continue operating under fundamentally different boundary conditions. PIXL's elemental analysis reveals trace element patterns in Martian rocks that indicate mantle source compositions surprisingly similar to Earth's primitive mantle before extensive crustal recycling and plate tectonic processes modified the planet's interior chemistry through billions of years of geological evolution. The rare Earth element signatures suggest that both planets accreted from similar nebular materials and underwent comparable early differentiation processes. Yet Mars apparently ceased major geological activity much earlier than Earth, due to its smaller size and more rapid heat loss through surface radiation. This comparative perspective transforms understanding of planetary evolution from unique individual histories to variations on common themes determined by fundamental physical parameters, including mass, distance from the Sun, and volatile inventory. The clay mineral assemblages detected throughout Jazero's geological formations indicate water-rock interaction processes that operated through mechanisms identical to those producing similar alteration products in terrestrial weathering environments. Yet the Martian examples formed under atmospheric and climatic conditions that have no modern analogues on Earth. Montmorillonite, kaolinite, and other phyllosilicate species form through specific temperature, pH, and chemical activity conditions that apparently existed on early Mars despite the planet's current hostile surface environment. These shared mineralogical processes suggest that habitable conditions might develop through similar mechanisms on other rocky planets where liquid water achieves stability, expanding the potential for finding life beyond the solar system. Comparative atmospheric chemistry reveals fundamental differences in volatile evolution between Earth and Mars that influence long-term habitability, despite similar initial water inventories and atmospheric compositions inferred from isotopic analyses of Martian meteorites and atmospheric measurements. Earth's larger mass and stronger magnetic field enabled atmospheric retention and plate tectonic recycling that maintained surface conditions suitable for liquid water throughout geological time, while Mars lost most of its atmosphere to space through solar, wind stripping, and achieved equilibrium surface conditions hostile to biological activity within the first billion years of planetary evolution. These divergent atmospheric histories demonstrate how planetary mass and magnetic field strength determine long-term habitability potential. The organic compounds detected in Martian sedimentary rocks provide the first direct evidence for carbon chemistry operating on another planet, under environmental conditions different from Earth. Yet the molecular signatures remain consistent with both biological and abiotic formation mechanisms that operate in terrestrial hydrothermal systems and sedimentary environments. This chemical similarity across planetary boundaries suggests that organic synthesis represents a fundamental aspect of rocky planet evolution, where carbon, hydrogen, oxygen, and other biogenic elements achieve sufficient concentrations and appropriate reaction conditions. The ubiquity of organic chemistry strengthens arguments for potential biological activity throughout the solar system and beyond. Isotopic compositions measured in Martian atmospheric gases and rock samples reveal fractionation processes that operated through mechanisms similar to those influencing Earth's isotopic evolution. Yet the Martian values record different source materials, atmospheric loss processes, and chemical cycling histories that reflect unique planetary characteristics. Oxygen isotope ratios indicate meteoritic contributions distinct from Earth's accretionary materials, while carbon isotope signatures suggest atmospheric evolution dominated by volcanic outgassing rather than biological carbon cycling. These isotopic differences provide quantitative constraints on planetary formation processes and volatile cycling mechanisms that operated throughout solar system history. The hydrothermal alteration products identified in Martian volcanic rocks indicate subsurface water circulation systems that operated through heat and mass transfer processes identical to those creating similar mineral assemblages in terrestrial geothermal environments. Yet the Martian examples formed under planetary conditions including lower gravity, different atmospheric composition, and potentially different heat sources that influenced fluid circulation patterns and chemical reaction pathways. The preservation of hydrothermal textures and mineral assemblages demonstrates that subsurface habitability might persist long after surface conditions become hostile, providing refugia where biological activity could continue during planetary climate transitions. Spectroscopic analysis reveals mineral formation sequences in Martian igneous rocks that follow crystallization pathways predicted by experimental petrology and thermodynamic modeling based on terrestrial volcanic systems, confirming that magma physics and mineral stability relationships remain constant across planetary environments despite different gravitational fields, atmospheric compositions, and volatile contents that influence eruption styles and cooling histories. This universality of igneous processes enables direct application of terrestrial geological knowledge to interpreting Martian volcanic evolution while highlighting the fundamental physical principles that govern rocky planet development throughout the universe. The comparative planetology perspective transforms individual Martian discoveries into broader insights about planetary habitability, geological evolution, and potential for life that extend beyond the solar system to guide understanding of exoplanetary characteristics and astrobiological potential in stellar systems throughout the galaxy. Each measurement by Perseverance's instruments contributes to a growing database of planetary process variations that reveal how different boundary conditions influence geological and potentially biological evolution while operating through universal physical laws that connect Earth's history to the broader cosmic context of planetary development and habitability potential. Only took 60 years of planetary exploration to develop analytical capabilities sufficient for conducting comparative planetology studies that reveal universal geological processes operating under diverse environmental conditions throughout the solar system, demonstrating how robotic exploration expands understanding of planetary evolution and habitability beyond the limitations of terrestrial analog studies and laboratory experiments. The long wait home begins as sample tubes rest in Martian regolith like buried treasures from an ancient civilization, their titanium walls preserving geological specimens that will journey across interplanetary space aboard spacecraft still existing only in engineering blueprints and mission planning documents that evolve through design reviews and budget negotiations spanning multiple years. Each cached sample contains billions of years of planetary history compressed into cylindrical volumes measuring centimeters in length, yet representing scientific value that exceeds most national research expenditures as humanity prepares for its most ambitious robotic exploration campaign involving multiple space agencies, cutting-edge technologies, and international cooperation unprecedented in planetary science missions. The specimens await collection by sample retrieval landers that must achieve precision landing accuracy approaching individual tube dimensions while operating autonomous systems across communication delays that prevent real-time control from Earth. The Mars sample return architecture requires coordination between 3 separate spacecraft missions that must function flawlessly despite launching years apart and operating under environmental conditions that challenge every engineering system, from solar panels exposed to cosmic radiation to mechanical actuators operating at temperatures approaching absolute zero during Martian winter nights. The European Space Agency's Earth Return Orbiter will establish orbital infrastructure for receiving samples launched from Mars' surface, while NASA's Sample Retrieval Lander deploys collection rovers and Mars Ascent Vehicle systems that must locate cached tubes, transfer them to pressurized containment systems, and launch them into Martian orbit with trajectory precision exceeding any previous interplanetary operation. These technological achievements represent decades of engineering development and hundreds of billions of dollars in mission costs distributed across international partnerships. Sample preservation requirements extend throughout multi-year mission timelines as cached specimens endure temperature cycling between -80 degrees Celsius during winter nights and 0 degrees during summer afternoons. Cosmic radiation bombardment equivalent to tens of thousands of chest X-rays annually, and atmospheric pressure variations that accompany seasonal carbon dioxide condensation and sublimation at Mars's polar caps. The titanium storage tubes resist corrosion by perchlorate-rich soils and maintain hermetic seals despite thermal expansion effects and mechanical stress cycles that would compromise most terrestrial storage systems within months of exposure to Martian environmental conditions. This preservation technology enables sample integrity maintenance during storage periods that could extend beyond planned retrieval timelines if mission delays or technical challenges postpone sample return operations. Each cached tube contains headspace gases that preserve atmospheric samples collected simultaneously with geological specimens, creating combined solid gas archives that provide insights into current Martian atmospheric chemistry while enabling laboratory analysis of volatile compounds using analytical techniques unavailable on rover platforms. The atmospheric preservation aspect transforms individual rock samples into comprehensive environmental archives that record both geological formation processes and contemporary atmospheric conditions, doubling the scientific return from sample catching operations while providing calibration standards for interpreting rover-based atmospheric measurements and orbital remote sensing observations. The interplanetary trajectory calculations required for Mars sample return involve gravitational dynamics, orbital mechanics, and spacecraft propulsion systems operating across solar system distances where navigation errors measured in meters at Mars translate into orbital insertion failures and mission loss scenarios that motivate redundant guidance systems and backup trajectory options. The launch window opportunities occur every 26 months when Earth and Mars achieve optimal geometric alignments for minimum energy transfer trajectories, constraining mission scheduling and requiring precise coordination between sample collection, ascent vehicle operations, and orbital rendezvous procedures that must synchronize across multiple years of mission development and execution phases. Contamination prevention protocols ensure that returned samples maintain scientific integrity despite exposure to terrestrial atmospheric conditions, spacecraft outgassing products, and handling procedures that could introduce Earth-based organic compounds or microbial contamination that would compromise astrobiological analyses seeking evidence of indigenous Martian life. The sample receiving facilities under development employ biological containment systems more sophisticated than those used for hazardous pathogen research, creating sterile laboratory environments where returned specimens undergo initial characterization and distribution to research institutions worldwide while preventing both forward and backward contamination scenarios that could compromise scientific objectivity or planetary protection requirements. Advanced analytical techniques awaiting sample return include isotopic analysis with precision exceeding rover instrument capabilities by factors of 10,000, molecular structural determination through synchrotron X-ray crystallography, and microscopic examination that can resolve individual bacterial cells and organic molecular structures within mineral matrices if such biosignatures exist in the returned specimens. These laboratory capabilities enable detection of trace organic compounds at concentrations measured in parts per trillion while preserving spatial context and mineralogical associations that provide essential information for distinguishing between biological and abiotic formation mechanisms. The scientific impact of returned Martian samples extends beyond astrobiology to encompass planetary formation processes, solar system evolution, and comparative planetology studies that inform understanding of exoplanetary characteristics and habitability potential throughout the galaxy. Laboratory analysis will reveal detailed chronological information about Mars's geological evolution, atmospheric history, and environmental transitions that influenced habitability during the planet's early history, when liquid water flowed across surface landscapes that now exist only as frozen sedimentary archives and mineral alteration products. These temporal constraints provide calibration points for planetary evolution models that guide interpretation of exoplanet observations and assessment of habitability potential in stellar systems throughout the universe. International collaboration frameworks developed for Mars. Sample return establish precedents for future cooperative missions that exceed the technical capabilities and financial resources of individual nations, demonstrating how scientific objectives can motivate sustained international partnerships despite political tensions and economic competition that characterize terrestrial diplomatic relationships. The shared costs, complementary technologies, and distributed expertise required for sample return operations create models for ambitious exploration programs, including human Mars missions, outer planet exploration, and interstellar probe development that represent humanity's next steps in cosmic exploration. The cached samples rest beneath alien skies where Earth appears as a pale blue point of light among the stars, waiting for collection by spacecraft that will carry them home across millions of kilometers of empty space to laboratories where researchers decades in the future will search for answers to questions about life's existence beyond Earth. These titanium time capsules preserve chemical signatures and geological textures that might represent humanity's first physical evidence of extraterrestrial biology. Or, alternatively, confirm the rarity of life in universe where planetary conditions suitable for biological activity prove exceedingly uncommon despite the abundance of rocky worlds orbiting other stars. The patient samples await their cosmic journey home while Mars continues its ancient rotation beneath skies that have witnessed volcanic epochs, impact bombardments, climate transitions, and perhaps even the emergence and extinction of microbial ecosystems during the planet's early history when environmental conditions resembled those that supported life's emergence on Earth billions of years ago. The whisper of Martian wind carries dust across sample depot sites where titanium tubes rest like metallic prayers offered to the cosmos, their sealed chambers holding secrets that bridge worlds separated by hundreds of millions of kilometers and billions of years of divergent planetary evolution. The rover's instruments fall silent as power systems conserve energy for essential operations, their sophisticated sensors having transformed alien geology into quantitative datasets that will occupy researchers for generations, while raising new questions about planetary habitability and the potential for life beyond Earth's protective atmospheric envelope. Shadows lengthen across Jezero crater as the distant sun traces its familiar arc through salmon-colored skies, where water vapor exists only as trace constituents in an atmosphere too thin to sustain the liquid oceans that once filled this basin with standing water deep enough to support complex sedimentary processes. The ancient lakebed preserves chemical signatures of environmental conditions that have no modern analogues. Yet the preserved mineral assemblages and organic compounds suggest that early Mars operated through geological and possibly biological processes remarkably similar to those characterizing Earth's most extreme environments, where life persists despite conditions that challenge conventional understanding of habitability limits. Each sample cache represents a convergence of technological achievement and scientific curiosity that spans decades of mission planning, engineering development, and international cooperation focused on answering fundamental questions about humanity's place in a universe where rocky planets orbit billions of stars throughout galaxies that stretch beyond observational horizons. The cached specimens await collection by spacecraft that exist currently only as engineering concepts. Yet their eventual return to terrestrial laboratories will mark humanity's transition from studying other worlds through robotic proxies to conducting direct laboratory analysis of extraterrestrial materials collected specifically to address questions about life's cosmic distribution and the geological processes that create habitable environments. The red planet continues its eternal rotation beneath skies that have witnessed volcanic epochs when lava flows carved channels across highland terrain, impact bombardments that excavated massive crater systems, and climate transitions that transformed a world of rivers and lakes into the frozen desert that challenges every mechanical system humans have managed to land successfully on its surface. Perseverance rests among geological formations that preserve 4 billion years of planetary history in sedimentary layers and igneous compositions that record environmental conditions existing when Earth possessed no continents, no complex life, and no technological civilizations capable of exploring other worlds through robotic extensions of human curiosity and scientific methodology. The analytical instruments that revealed elemental compositions, organic molecules, and ancient water signatures now enter dormant states as mission priorities shift towards sample preservation and communication with Earth across interplanetary distances that require patience measured in geological rather than human timescales. The scientific discoveries accumulate in databases where digital reconstructions preserve textural details, chemical compositions, and environmental context with fidelity that enables virtual exploration by researchers who will never experience the thin atmospheric pressure, temperature extremes, and cosmic radiation that characterize daily existence on Mars' hostile yet scientifically fascinating surface. Dust accumulates on solar panels and instrument covers as global atmospheric circulation redistributes iron oxide particles across continental distances, creating the characteristic reddish coloration that has inspired human imagination since ancient astronomers first noticed the planet's distinctive appearance among stellar constellations that served as navigation references for civilizations that flourished and disappeared while Mars underwent gradual atmospheric loss and surface desiccation. The planet's geology preserves records of this atmospheric evolution in isotopic signatures and mineral assemblages that document the transition from early warm and wet conditions to current cold and dry environmental states that nonetheless support ongoing geological processes, including dust devil formation, seasonal frost cycles, and perhaps even trace gas emissions that continue to puzzle atmospheric chemists. The rover's nuclear power source maintains minimal operations through radioactive decay processes that will continue generating electricity long after communication systems fail and mechanical components succumb to thermal cycling and radiation damage that gradually degrades electronic circuits and mechanical actuators exposed to environmental conditions more extreme than any terrestrial analog. This nuclear persistence ensures that some rover systems could theoretically function for decades beyond planned mission durations, creating the possibility that future human explorers might encounter still operational scientific instruments deployed by robotic predecessors that initiated humanity's systematic exploration of Mars through increasingly sophisticated analytical capabilities. Time moves differently on Mars, where sols extend slightly longer than terrestrial days, and seasonal cycles span approximately twice Earth's annual duration, creating temporal rhythms that influence atmospheric dynamics, temperature variations, and chemical processes operating on timescales that connect geological and astronomical phenomena across cosmic distances. The planet's orbital mechanics link its environmental conditions to solar system dynamics that govern planetary heating, atmospheric circulation, and seasonal variations that continue operating through physical principles that remain constant throughout the universe, regardless of whether conscious observers exist to measure and interpret these natural processes. The cached samples rest in patient stillness, awaiting spacecraft that will carry them across the cosmic void to laboratories where analytical techniques not yet invented will probe molecular structures and isotopic compositions, seeking evidence that life once emerged in ancient Martian environments that supported chemical conditions suitable for biological activity. Their metallic containers preserve geological time within human-engineered vessels that represent technological achievements connecting Earth's most advanced civilizations to discoveries that might reveal humanity's cosmic context and the prevalence of life throughout a universe that contains billions of planets orbiting other stars. Silence settles across the crater floor where ancient waters once lapped against sedimentary shores under skies that may have witnessed the emergence and extinction of microbial ecosystems before Earth developed complex multicellular life forms capable of eventually creating technologies sophisticated enough to explore other worlds and search for evidence of cosmic biological heritage. The samples sleep in Martian dust, dreaming of Earth